happy return. If you landed here, you're interested in trying to figure out what is the distance that you would have between a point, let's say, and a plane, or between a line and a plane. And of course, we're looking for the shortest distance because, okay, you can find infinite amount of distances if it's an infinite plane that you have in there, just by taking in any kind of distance or line that connects the point to the plane. So we are interested in the shortest distance. Now, that particular shortest distance, as you can see here, I have kind of showed it from 2 points of view. So here's a point, and now that shortest distance that we would have is basically from the point, okay, so touching, and it would be, I guess, the perpendicular drop, okay, from the point and the line that would touch the actual plane, and so what is that distance? Or if you have a line, and this will, by the way, only work with a line if the line is actually parallel, because if it's not parallel, then, you will either be having a distance of 0 because the line will actually go through the plane, or possibly the line actually lies on the plane. So I've talked about the intersection of lines and planes. I'll put up a link up above there. Now, in this one, I'll make the assumption that the actual line is parallel to the plane and it doesn't actually lie on the plane. So coming back to this point, let's take that as our starting point. So how in the world would we find this distance? Well, I know that if you have gone through math at some point, probably maybe in grade 10, you have calculated the distance from a point to a line. Now, in grade 10, when I used to do those videos, I'll put up a link to that exact video, so it might refresh your mind, okay, on how to do that. Now, we are going to be working with something similar, but now we have way more tools. So as you get into kind of grade 12, you started to do some vectors, okay, or maybe in first year post-secondary, you do have the tools of dot products, for example. That's one major tool. And you have some concept of, understanding angles, okay, between vectors. So I'm going to use that, okay, in order to solve this little problem of the distance from a point to basically a plane. So how would I do it? Well, we know that an actual plane can be written out in its standard or its scalar form, and therefore we can pick off the normal to the plane, right? So for example, I'm going to just do it on the side over here. So let's imagine that I have a normal, okay, which defines, so this is the vector, which is going to be perpendicular to the plane. Now, once I have this normal to the plane, what I want to be able to do is the following. So I have a point. Now, let's assume that we know what that point is. And I have, let's say, some equation of the plane. I'm going to assume that that equation of the plane, let's say, is in standard form. But it can be in vector form or parametric form. You can always change it back to the standard form. So when we have that, what I suggest that you do, and this is what textbook suggests, okay, often, and other teachers, okay, that I have run into, okay, the suggestion is that you do this. You say, okay, so since I have a point P, let us just find another point on the plane. So I'm going to find some point on the plane. So let's say, it's maybe somewhere over here. I'm going to call this point Q. So now I have the point P and I can find a point Q. Now I can of course find any point Q because I have the equation of the plane. And now if you draw, okay, you can actually create, okay, and this is a vector which is going to be the vector from P to Q, right? Or from Q to P, it doesn't really matter. So if I have this, let's assume that I'm going to call this the vector, which is going to be from the point P to the point Q. All right, so this is what I have. And I'm going to just draw it, okay, kind of in 2 dimensions over here. So let's assume that this is my actual point, okay? So this is from point P, this is to point Q, you know, and this is my vector that I have in here. And now my normal, okay, that I'll have, okay, and so this is my normal within there. So I'm going to put my, you know, normal somewhere over here, okay, and this would have been my normal, right? And I'm going to shift that normal, so I'm going to translate it so that it actually just is at the exact same point P. So if we wanted to find what the distance is, what the shortest distance is, because we know that the normal is actually perpendicular. So if we wanted to graph it and place it, so if I would take this and I would want to be able to place it, okay, so right there, right? Now, of course, you know, I'm gonna, you know, we can kind of shorten it so that it just kind of touches, okay, that particular. Okay, so there we have it, right? So let's say it's assumed that it was a perfect, okay, normal, that it would actually touch the plane itself. Now, it doesn't have to be, right? The normal can be anything, but we can, of course, scale it. So as you can see there, then really, that's what I am looking for. Now, that scaled version, and what I'm going to do, actually, so for this one, let me duplicate it, and I'm going to give it a different color. I'm going to shift it ever so slightly, okay, just a little bit off so that you can see it there and the actual dotted line. So what we're trying to really do is we're trying to find this vector's projection onto the normal, right? And if we would do that, so if I would just take this, right, and then drop this down all the way, because this would indeed be the projection, we would find this vector from the point P to the actual plane, which would be the shortest vector, okay, in this case, that is going to be touching that plane. But if we're interested in this actual vector, right? So if we're interested in this vector, then we can say, well, hold on. If I know what this vector would be, right, to be able to drop it down, and by the way, this indeed is the projection. So it is the projection of the vector PQ onto the vector N, right? That is the actual projection, right? That is the vector itself. But we've done projections. So I will put up a link up above there to projections if you've forgotten it, right? Now, what is the projection? Well, what did we need? We needed an angle here, right? If we knew what the angle was and we wanted to know what that projection would be, we would say that, oh, well, this is just, you know, kind of the magnitude of PQ that I would have, and it would have been multiplied by the cos of the angle, right, in between. And it would have been multiplying by whatever that vector n is. And of course, I need to take its unit vector, right? So I need to have it. So I'm going to divide it by the actual magnitude of that. And it would just scale that vector accordingly. So that would have been our projection. So that isn't anything new. Now you might say, ooh, doing this projection is going to be a lot of work. I'm just interested in the distance. Yeah, you are correct. We are only interested in the distance. So we don't technically need this, right? We don't need the actual vector itself. So the scaled version of the vector. We just want its magnitude, right? So we really are interested in just the magnitude of this thing because we want to know what the distance is. And by the way, if that normal, because the normal itself, it could have been in the opposite direction. That doesn't matter in this case. So if you remember the projections, it would have just given a negative value. And if you took the magnitude of that, it still gives you the actual distance. That's what we're after. So if I want the magnitude, I indeed can go back and think about, well, what was the magnitude, right? Like, how did we find it? Well, finding the magnitude in here just related it back to the dot product. So I could have just taken this on its own, okay, right here. Okay, I'm going to just duplicate it for us. So that is, let's say, the magnitude. Now I want to be able to find the actual magnitude of this. okay, on its own, well, I can, cheat a little bit. Not really, right? I can multiply this by the magnitude of this and divide it by the magnitude of my normal, right? This is exactly what we did in the projections, by the way. Now, the reason why I do that is just to make our life easier. So what we are now trying to do is we're trying to find that actual distance, right? So if you can intuitively understand the projection from P to Q, so that vector, onto the normal vector, which is going to give you the vector which touches the plane, and now you take the magnitude of it, so you're finding the distance of that vector, then you should understand what we're doing here. So that's exactly what I'm trying to do. And now with this multiplication by the magnitude of your normal vector, divided by the magnitude of the normal vector, that's just so I'm not changing anything, the actual numerator, so this itself, this is just the definition of the dot product. So really what this is saying is, okay, so take the dot product between these two vectors that you have and, take its magnitude, so as a whole, so you can take the magnitude of the entire thing and then divide it by the actual magnitude, okay, of this. And that gives you the distance. So this is the actual distance from the point that you would have to the actual plane, right? So this is exactly what we would have. So that is the formula. Now you can memorize the formula if you like, or you can think of it in terms of projections if you forget. By the way, I don't remember these formulas. Most of them I have to go back and kind of just think, okay, intuitively what it means, and then start to refresh my mind. Sometimes I even go back to my own videos to try to do that. So don't feel bad if you forget it. But always remember that, okay, do I understand what I'm trying to do here? Now, finding the dot product between two vectors is easy, right? Finding the magnitude of a vector is also easy, so that's not bad. So that's what we are trying to do here. So let's do this with an example. So here it is, okay? So here's my point. Here's an actual plane. Let's try to find out what the shortest distance to this plane is. All right, so that's something that we want to be able to do. Now, before you start, plugging away, right, and trying to find what the result is, you can, so number one, just check if the point P is actually on the plane, right, just to save yourself some time, because now it's highly unlikely that it is, but it might be. Okay, so you can check that, and that check is very easy. You can substitute the point into the plane and just check. So this is going to be 2 multiplied by 0 minus 1 plus 4 multiplied by 3 minus 1 is equal to 0. So let's see what the left-hand side gives us. So this is just 0. This is just minus 1 plus 12 minus 1. So I guess this is going to be definitely not equal to 0. This is just 10. So this tells us the left-hand side doesn't equal to the right-hand side. So this point is not on the plane. All right, so that's number one. Number two now is, okay, so now I want to find the distance. So what did we say? Well, so now find a point Q, right? And this point Q can be any point on the plane. So just choose them, randomly if you wanted to be able to see, what you actually need. Then you can choose your points, okay, at random in here. This will, of course, depend on what you have. So a very nice, okay, and easy way to do this is, let's say, choose, I will look at here. I'm going to choose x is equal to 0. I'm going to choose y is equal to 0. And what that is going to give me is the plane now becomes for z, because I substituted with these two. Minus 1 is equal to 0. Now let me solve for z or z. That's going to be 1 over 4. And so what that tells me is, okay, so I found 1 point. So 1 point, 0, 0. And this is going to be 1 over 4. So really this is just the z-intercept of the plane. So I have now a point Q. All right. So now number 3. So now here is your point P. So I have a point P. So that's my point P. I have a point Q. All right. So now I'm going to find. So this is going to be from P to Q. So I need to find this vector, right? So as you go from one to another. Doesn't matter which order, it can be Q to P. Okay, so that's irrelevant because at the end we're going to be taking the magnitude of it. So if it's negative, it matters not to us. So let's just work this out. So this is going to be, now we have to change the points to vectors. We have to subtract them so that we know what the actual vector, the difference of the vector is. So in this case, this is going to be just 0. It's going to be 1 minus, so that's 1. And then 3 minus a quarter. So I guess this is going to be 2. And I guess it's 275. So 2 3/4. So that's what I have as my vector. Now, number 4. Okay, so now that I have this, now you can find your normal vector. So your normal vector from here is just reading it out. So that's going to be 2, -1, and 4. So that's your A, B, and C values from your line. So this is from your standard, sorry, from your plane. So now I have that. And now I have basically everything that I need in order to do this. So number 5, you can now certainly find out what the dot product between them is. So this is going to be the dot product between P and Q right there. That's what I need, right? I will be taking the magnitude of this, and then I'm going to be dividing it by the magnitude of my normal vector. So, well, doing that, I'm going to just do this in fast forward fashion. So let's see what this gives us. There you have it. So the answer is 2.98. So it's approximately 3. Now it might have a unit, of course, you know, whatever this might be. So it's a distance, maybe it's millimeters, centimeters, whatever it is. We're using vectors, we're using Cartesian coordinates in here. So as a whole, so in 3 dimensions. So we didn't have any units, but it can certainly have units if you wanted to find them. And so notice, it doesn't seem very difficult. It's a little bit of work, but it's very basic work because it's dot products and then finding magnitudes of an actual vector. And you have your result. So that is it. So those are kind of the steps that you can follow to find what the distance might be from an actual point to a plane. Now, the other concept is, you know, what if you were trying to find the distance not from a point, but from a line? Well, this wouldn't be any different. So what you do is, in terms of trying to find the distance from the line to the plane, well, first you have to make sure that the line is not on the plane, or that the line actually doesn't intersect the plane, because then the shortest distance would be 0. But let's assume that it is parallel and away. Then just simply find an actual point, right? And that point, you know, you want to be able to find what that point is. Now you might worry, oh, you're choosing the point that is actually perpendicular to it. No, you know, you can choose any point, okay, within here. Now, please remember that, of course, this plane is infinite. So, you know, whichever point you choose, you're going to be finding it. Now, if I extend this actual plane and, you know, make it further and further, okay, as I go through, so it's going to be touching the actual, you know, it's going to be the shortest distance. That plane is infinite. So it doesn't matter actually which point you choose there. And, you know, once you do that, okay, well, just name it point P. So you need a point on the line. Now that you have a point on the line, you do the same thing. You do exactly the same process as you would from a point. So the only extra step is just find a point on the line. But if it's in 3 dimensions, it's going to be very easy for you to find the point, because in 3 dimensions, a line will either be in vector equation form or in parametric equation form. And from there, you have an initial point, okay, as you're starting off. So, for instance, you know, let's say that I had something like this. So here's my line, and here's my plane. So the first thing that I've mentioned, you know, the first thing that you should try to do is just check if this line actually intersects this actual plane, right? So we can do that. I'm going to just substitute this back in just to see, okay, what this will give me. So I need the value for x. So putting it back into parametric form, so x is equal to 1 minus t, right? So that's 1 minus the t. Then it's going to be minus 2. My y is going to be 1 plus 5t, so that's that. And then plus, and then 5, and then my z is 1 plus, well, this one is annoying, 13 over 5t. And then minus 2 is equal to 0. Now I got to work this out, so I'll do it in fast forward fashion. Hold on. We come down to this. So basically, we have this. So this line will not intersect the plane, so it is actually parallel to it. And because left-hand side will never equal to the right-hand side, so we actually do know that we have a plane and we have a parallel line. All right. So again, if you've forgotten it, you can go back to that initial link that I started the video with to look at the intersection of lines and planes. Now that you have this, well, now you just need a point. Well, you might as well set t is equal to 0 and then get your point. So your point can be this. So now number 2, just get your point P. So that's going to be 0.111. It's the easiest one that you can find there, or at least the quickest one. And then from here, you will do exactly the same process. So, step 3, find your Q, whatever that Q might be. Okay, once you have your Q, you can do, P minus Q. So to find your vector, you will find and read out your normal vector. So here it is. It's going to be 3, negative 2, 5. You're going to take afterwards the dot product in between them, take the magnitude and divide by the magnitude of the normal. And there you have the distance from the line to the plane. So I'm not going to go through this whole process. I'll actually leave it for you, right? So you can give this a try. And as I've kind of finished the video, I'm going to put the answer, okay, there for you. So if in case you are trying, this would have been the actual distance. Okay, so I'm going to do that and put it in the video, okay, for you. And that is it. Right? That's all that you have with respect to these. So the projections do help. And if you do understand the meaning of the projection, okay, then it makes sense to you that this is the way to find the fastest way, the shortest distance, right? So you don't have to do any chaotic stuff if you're familiar with projections. All right, so thanks for watching, and hopefully we'll see you in a future video. Bye, everybody. Cheers.